Okay, so this is the EDCI DC circuits parallel 1 exercise that we're going to look at. All right, so first of all, what's different about parallel circuits from series circuits? There are multiple paths for current to flow, okay? And I told you before, in a series circuit, what was our constant across all the wires? Was current. Well, now we're in a parallel circuit and our constant is voltage. All right? And so if we want to calculate total resistance of a parallel circuit, here's our formula right here. Reciprocal of all of the resistors plus the reciprocal. So you're going to take reciprocal twice. All right? So let's look at this. So here I have a sample circuit, and if we want to calculate total resistance, our formula is 1 over RT equals 1 over R1, 1 over R2, etc., depending on how many you have. So in this example here, we are going to calculate 1 over 820, 1 over 560, and then 1 over 470, okay? And once we do that, we come up with these values below here, all right? Come up with this, and once we add all of those up, we divide by 1, right here, divide by 1, all right? And this gives us our total RT of 194 ohms. Everybody see how we did that? Here, we're going to do an exercise here in just a second, all right? All right, so what we need to do in this example is we want it to, if our voltage, in this example our voltage is given, so that's going to be our constant. When we pick our Ohm's law formula, let's try to pick one with voltage in it. So we know what RT is and we know what V is, so now we can simply use Ohm's law to calculate current, okay? So we have 12.3 volts given right here, 12.3, all right, divided by RT, which we calculated earlier, all right, right here, and that gives us 63.135 milliamps. You see that? All right, so how do I calculate the individual current across each resistor? Because each one of these resistors is what? A kink in the hose, right? Okay, and depending on the resistor value is how much a kink there is in the hose to let the water through, or electrons if you want to look at it this way. So up here on our little circuit, we have 3 resistors. We have 820 ohms, we have 560 ohms, and we have 470 ohms. Which one is the biggest kink in the hose? 820, all right? So we would assume that the one with 820 ohms would have the least amount of current across it, all right? Remember that our current across R1, R2, and R3 must add up to our 63 milliamps. Kirchhoff's law, okay? All right, just checking I didn't have the microphone muted on that. So now we're going to calculate our individual current across each one, all right? And simply substituting our standard Ohm's law formula for current, V over R, okay? We are going to substitute, instead of using RT, we're going to use R1, which gives us each one of our individual current consumption across each one of these resistors, okay? So we have the 820 is 15 milliamps, all right? The 560 is 21.96 milliamps, okay? And as we go down, we'll see that, oops, let's see that. not showing the other one. But we'll see that as we have a larger resistance, we have a bigger kink in the hose, which means we have a smaller amount of current go across that, right? So our 470 ohm has the largest amount of current that goes across it, right? All right, because it's not as kinked as everything else. All right. So that being said, let's do some practice examples on the board and solve. What do we have here? All right. Here's a blow up version of that, simply using Ohm's law to calculate each one of the milliamps. Notice that the 470 ohm has the least amount of resistance, so it draws the most amount of current. All right. Now, right here at the bottom, the sum of the branch current should be equal to the total current. Are you with me? And it's showing we added up each one of these branch currents to a total of 63.13 milliamps, which was our IT earlier. Okay. Now, parallel circuits, as we said before, that's going to be your standard circuit pretty much in everything. That's how we wire our houses. That's how this classroom is wired, because what that does is it provides a constant voltage to our devices. All right. Trust me, you don't like, modern electronics do not like a variance of voltage. They can tolerate a little bit, but they must have a constant voltage to perform correctly. All right. Plus, in a series circuit, we kind of know if our lights were wired in a series circuit like a Christmas light, and one of the bulbs went out in your house, you'd have to figure out which bulb in your house was burnt out. How many bulbs you have in your house? I don't know. More than you want to check. All right. Now, here we have our voltage drops, and we don't have to do any calculations because they're going to be the same, right? Now, what about power? How do we calculate power across each one of these? Now, yesterday we looked at our little circuit and how we upped the voltage, and the current went up, and we could see that certain resistors got warmer than others, okay, because of the power dissipation. All right. So in our circuit yesterday, which was the warmest resistor of all three?
Smallest.
The smallest one got the warmest, because we did the calculation so we could only pass through almost 1 watt, not quite. We didn't want to burn up our resistor. And the smallest value resistor got the warmest at, I think, 10 volts. So simply calculating power is pretty much the same. If you know your IT and your VT, you can calculate power right here. All right. Now, in order to calculate the individual power requirements across each resistor, simply substitute the individual current. All right, IR1. All right, and over here, IR1 would equal the current across this 820 ohm resistor. All right, and then we move on down to calculate PR2. All right, it's going to be the current PR2, 21.96 milliamps across this one. All right, so forth and so on until we come up with these three values. And guess what? Once we add them up, they should equal power total. All right, same thing with current total. All right, we clear on that? Let's actually do something. We'll see how clear we are. Okay. How are we going to calculate RT right here? All right. What's our formula?
1/1/4 dioda resistance.
All right.
Or receptacle resistance.
So this formula here, and this is going to be your formula sheet on your test, RT equals 1/1/4 each one of these resistive values, which is R1 plus 1 over R2 plus 1 over R3. All right? And so if we do those calculations, let's see what we come up with.
186.67, or, oh. It's okay, mine.
No, it might be a little different. We've got 470 ohms. All right, so if we want to solve for that, we would have 1 over 470, all right, plus 1 over 1500, plus 1 over 560. So let's find out what that is. Let's add them up.
218.33.
1 divided by 470. 0.002 plus 1 divided by 0.0006 plus 1 divided by 560 equals 0.00178. We add all of these up. All right. What do we get? What do we get when we add all of these up and then take the reciprocal? What is RT?
I got 218.33.
318.
218.
218. Okay. All right. Let's see what we got here. 218. You said 0.33.
Yes.
All right. And let's check our answer. You are correct. All right. Don't know what that's about. Technical difficulties. What formula do we want to use for IT? We already know VT, right? So let's just simply use Ohm's law to calculate the total. So I equals E over R. So that's 12 volts divided by, or 12.6, I'm sorry, divided by our total resistance of 218.13. It gives us
7.7 milliamps.
Yes, it gives us 0.057. So if we move it 3 decimal places, we have 57 milliamps. All right, I'm going to go ahead and carry it out a little bit more. 57.7. Probably get us there. And let's check our answer. We are correct. All right. So what formulas do we need to use to calculate the individual current across IR1?
The same one.
All right. Well, we can use the same one, except we're going to substitute, instead of using our RT, because this is total, right?
Mm-hmm.
We're simply going to substitute the individual. So let's see. Let's come down here and let's say that if we want to calculate the individual ones, we'll say I cross R1 equals E, or voltage total, divided by R1. And we'll substitute the numbers in there for each one of those values. So on the first one, let's just solve the first one. We're going to solve this one here. Let's say we're going to take 12.6 and we're going to divide it by the resistance value of R1. So 12.6 divided by 470 ohms. Okay, gives me a current of 0.026 amps. I'm going to say it's going to be 26.8 milliamps. That's what it's asking for. So we'll do 26.8 amps. And we'll check that. Oops. Backspace. And we'll check that. And that says correct. All right. And so if I want to solve for the next one, I would substitute my 470 ohms here. For R2, which is 1500 ohms. This is voltage. For this one, gives me 12.6 divided by 1500, gives me 8.4 milliamps. All right. 8.4 milliamps. We'll check that, and that is correct. So, on this last one, let's do something different because we're going to use Kirchhoff's law, and we only have 3 values. So, let's try Kirchhoff's law on this last one. Just to prove a point. We're kind of double checking our answers, right? Because if we screwed up on one of these calculations, if we didn't do it correctly, then our IT, these values wouldn't equal IT. So let's take 26.8 plus 8.4 milliamps. So that's 26.8 plus 8.4 milliamps equals 35.2 milliamps. All right. So I'm going to take my total, which is IT, and I'm going to subtract 35.2. Which gives me a IR3 value of 22.5. Get this up. All right. 22.5. Oops. And let's check our answer. We are correct. So here we've calculated the last one by simply adding up IR1 and IR2 and subtracting it from IT. What's VR1?
12.6.
12.6. And the same for the rest. Okay, so how do I calculate power total here?
Total.
Any number of ways, right? Pick one.
Current.
What's an easy one?
Total current. Okay.
It's an easy one. Go ahead.
Voltage. Current.
All right, so voltage times current. So here we want to calculate this one would equal voltage E times I, which is 12.6 times our IT. Remember, we're going to do, it's wanting a total here, so let's do an IT right there. All right. Times, remember to convert milliamps over to amps, 0.0577 equals 0.7270 watts. And if we move the decimal place three places, we have 727 milliwatts for our total. So here, we're going to calculate 727. I think that'll work. Let's check that. And we are correct. All right. So now we're going to repeat those steps here for PR1, PR2, PR3. So here we're simply going to substitute our individual current drops. So here we have our voltage total, ET, times the individual current used across R1, which we see up here, is 26.8. So we're going to do that with 26.8 milliamps. And that would be I, little r1. And we would repeat this with each one of these to give us our answer. So let's see how that works. We're going to do 12.6 times 0.0268, because we have to move decimal point, which gives us 337 milliwatts. So let's see what we have here. All right, so what's PR2 and PR3? All we have to do for the next ones are substitute equals E T times I R2 ET times I R3.
The next one is 105.
How much?
105.8.
105.8 milliwatts.
Yes.
10. All right, and what's the last one?
$283.5.
283.5. All right, check that, and it is right as well. Now, how would I double check these answers, because it's showing us as we check individually how we can do that. Well, what is this? PR1. So PR1 plus PR2 plus PR3 equals power total. Right? If we add all those up, they should equal 727 milliwatts. All right. Are there any questions about that so far? All right, let's stop the stream and we'll go from there.